organizers for the invitation to this very nice workshop. Greatly enjoy being here. I'm going to speak about some results concerning volumes of random sections of lpn-balls, and this is based on joint work with Pivovarov and Simanjuntak, both from the University of Missouri. So let me start with some motivations. So clearly, sections of convex bodies, either by deterministic or random subspaces, will play an important role in many results in asymptotic geometric analysis, and most of theorems that we see there are either some inequalities or comparison, for example, of average volumes of such random sections for different bodies, or perhaps two-sided inequalities, or first-order behavior. So this first-order behavior may be understood for the expectation or improbability. On the other hand, we have stochastic geometry, and as we have seen, well, you all know that, but we have also seen this in this workshop. There are a lot of results for volumes of various random convex sets. For instance, random convex house in many settings, for example, fixed or growing dimensions. And there, of course, there are also inequalities and approximations to the expectations or the laws of large numbers, but they are usually complemented with further results like small vol probabilities or large deviations, which we saw in this workshop, or the study of fluctuations. It may be for the volume or in some settings for the log volume. So our motivation was to sort of look at those results from asymptotic geometric analysis, at some of them, and try to complement those first-order results with some limit theorems. So more specifically, we would like to look at the lpn-balls. They appeared on the first day in the talk by Tomek. So this is the usual definition with the usual interpretation for p equal to infinity as the cube. And we're going to look at sections by random subspaces. And when I say random, I always mean uniform on the Grassmannian of fixed codimension. So the codimension D will be here fixed, and the dimension of the lpn-ball n will tend to infinity. So these sections are high-dimensional random sets. They are, of course, star-shaped, and we will be also looking at the non-convex case for p between 0 and 1. Okay, so why lpn-balls? The honest answer is that, well, you have to start with something, and here you have many tools. Right? So it's reasonable to start with this case, but there are also some other reasons. So, of course, it's natural from the functional analytic perspective to look at such balls, but also there is a context to it, because there's been a lot of results either of geometric or probabilistic nature over the last 30 years. Like random vectors uniformly distributed on those balls serve like as a model of dependent random variables, which nevertheless often behave like independent. And also there is hope that perhaps this case will really reveal some phenomena which can be generalized later. So CLT for convex bodies was first obtained in this case. Also some negative association properties, for instance, were first studied for such balls. Okay, so we are interested in the behavior of such random sections. Let me recall again that the codimension is D and it is fixed and n tends to infinity. So first we would like to look at the first order behavior. So we have such a formula. Here it is somewhat implicit because I put the volume of the ball here. I will recall the formula for it in a moment. But okay, we have something like that. It holds with high probability as n tends to infinity, and also it holds for the expectation if I take the average of the randomness here is on the left-hand side. And this was first proved in expectation by Kądropski and Lifshitz. They were using Fourier analytic methods. But the high probability bounds are a specialization of a much more general result, which was obtained by Eldon and Clartak. So Clartak had this famous central limit theorem for convex bodies, and originally he was looking at some Kolmogorov type distances between densities of projections of isotropically concave vectors on subspaces of small dimension and the Gaussian distribution there. But together with Eldon, they also obtained they also obtained a result, a pointwise result for densities. So it's a very general result. This will be a special case. Let me recall you what it says. So if we have an isotropic concave random vector in Rn, and isotropic to me means that it is of mean zero and the covariance matrix equals to identity. It does not mean rotational invariance, right? Just covariance matrix equal to identity. So we may think just of uniform distribution on a convex body. We look at the projection on a, for the moment, fixed subspace now of dimension n, and it has a density there. So then when we randomize this subspace and look at it as a random subspace on the Grassmannian, then it turns out that the ratio of our density there and the standard Gaussian density on this subspace is bounded for x even. So here you can see it's a strong result. The dimension may grow to infinity, I mean the dimension of the subspace with n. X, where you look at this density ratio, also may tend to infinity. And what we are interested in is, in fact, fixed D and special case of the ball, not general convex body, and x equal to 0. So this is much more general. This bound implies the top one because, of course, the density of this projection, in the case of the uniform distribution on a convex body, is just the properly normalized volume of the section in the perpendicular section by the perpendicular subspace. Right? So here we will get something like that. You can see like this Gaussian density 2pi and the power here, and the rest is just a rescaling because our lpn-balls are not isotropic, but they are one-symmetric, so it's enough to rescale them. So this is the factor by which you have to rescale them to apply this result. Okay, so maybe let me go back. So this holds with high probability, but it's not clear how to pass to some conjecture, say limit theorem. So it will be more convenient to look at a normalization which for d equal to 1 appeared already in Tomek's talk. It's good to normalize this random volume by a volume of the ball in smaller dimension, or by the volume of the section, coordinate section, if you prefer such interpretation. And taking into account what the volume of the BPN ball is and what we had on the previous result, it turns out that such a ratio converges in probability to some constant depending only on P and T. So our goal would be to complement this convergence in probability with a limit theorem. And before I formulate the results, let me tell you when we can do it. So we can do it for arbitrary d for p smaller than 2. And our proof is quite involved. I will show you some elements of this proof. Probably it's too involved. Probably can be done in a more straightforward way. And we can do it with a somewhat simpler proof. It's fairly easy if you have the right tools, but the tools are classical tools from probability. We can do it for any p, but just for codimension 1. And it seems to us that the second proof should generalize, but there is one ingredient which is not present in the literature, and we use it just as a black box. So perhaps it's a nice problem to investigate if one can obtain this ingredient. I will come back to it later. So let me state the first result. And this is for p between 0 and 2. One would think at first that the result should be of the form, you look at your random variable, subtract the limiting value, and then you have fluctuations. It's not the case here. You have subtract one additional term, which is n-dependent, it converges to 0, and then the fluctuations are at the order n to minus 3/2. So this limiting variance is positive here, so this is the right order. And I wrote it in this way without making those constants explicit to have a compact formulation, but well, I should show you those constants. So you have already seen APT on the previous slide, but I don't know if you remember it. I don't, honestly, but well, let me show you it again and the remaining two beauties. So here they are. So okay, one could stare for hours, but we don't have time for this. So let me just make, they will disappear in a moment, let me just make some comments. So as expected, as it should be, for b equal to 2, a equals to 1, and b and sigma vanish. So they vanish because of this, common factor here. It vanishes for when you use the properties of the gamma function. You will see that it vanishes for b equal to 2, as it should, because of course it is the trivial case. Okay, so this is the result. Some further remarks. The convergence actually holds in all Wasserstein distances. So I'm not going to speak about those distances. I'm just mentioning this because it implies in particular convergence of moments. So when you apply it to the expectation, you get some refinement of this Koldovsky-Lifshitz asymptotics. So here this prefactor is this normalization written explicitly, and it was just APD plus O of 1 before. Now we can complement it with some second term. And in the proof of this result, well, one can track the constants and see how they emerge, but it's rather difficult to give them any reasonable interpretation. The softer proof for d equal to 1 gives an interpretation, perhaps not in geometric terms, or at least I cannot interpret it in geometric terms, but it relates it at least to quantities which appear somewhere else. So we will see it later. Okay, so this is the second result. This is the same, but d equals to 1, and p is arbitrary from 0 to infinity. Right? So here, with this second proof, we don't have this convergence in Wasserstein distance because of the nature of these tools that we use. And for the cube, we can look at non-central sections also. So we can move this hyperplane with slice width along the perpendicular direction. It's just one direction because codimension is 1. And you will see that the section depends on this x here. Also, the normalization here is slightly different because, well, when you fix p and d, when you fix p, just p, there is a difference between the case of p smaller than infinity. The volumes decrease rapidly to 0 as the dimension grows, and here for the cube, of course, it's not the case. So this normalization is here more natural. Okay, so a few words about tools. So the problem with studying those high dimensional, or in this case even small codimensional sections, is that, well, you have to look at volumes of bodies which are in high dimensions. So you could write some integrals, but it's difficult to see, to analyze them, right? So we need some volume formulas which would allow us to give interpretation to those volumes in a different way. And luckily for us, Piotrek and Tomek, a few years earlier, started investigating deterministic sections of lpn-balls and started looking at those extremal cases as we saw in Hausdorff, which is more difficult than this random case. And to to do this, they developed several formulas for volumes, so we could just use them. This is not the more general form of those formulas. They could rescale those balls in various directions, but here is the version that we will use. So we have our subspace of codimension D, and in the orthogonal complement, we have the orthonormal basis of cardinality D. So we align those orthonormal vertices as rows of a matrix. So this is a D by N matrix, and so when we look at the columns of this matrix, we denote them by VI. So we have N of them. And then the volume, already normalized, like we want to have it, is given by some prefactor, and, well, the expectation of the negative square root of a certain determinant. And the randomness comes from those IID variables Wj. How are they defined? Let me first recall that the standard positive alpha stable variable is defined in terms of Laplace transform. And such a variable, it has density, and it has good integrability properties. It has all moments, positive moments up to alpha, and it has all negative moments. In particular, when we divide this density by square root of x, it will be still integrable, and we can normalize it to create a probability density, and this is the density for our Wj's. So maybe one remark which we will use later. So this division by square root of x does not spoil negative moments, because all of them existed for y, but it improves integrability for positive moments. So we have at least 1/2 plus alpha here. And then we will be looking at the reciprocals, and it will be reversed. Okay, so this is the first volume formula. There is another volume formula which we will use just in codimension 1 for the second result. And it is also obtained by Piotr and Tomek, this time together with Yorgos Chasapis. So the setting, let me state it for generality. So the setting is the same. H is our subspace. UIs form an orthonormal basis in the orthogonal complement, and VIs are those rows of columns of matrix with rows UI. So here we have different random variables, also IID, but with different distribution. So this BP is just some constant involving, again, gamma functions. And then it turns out that our normalized volume of the section is given to the value at 0 of the, I should say, continuous version of the density of such random combination of those vectors VIs. Right, with this IID. So we will come back to it later. Okay, so let me show you some elements of this more involved proof, and maybe I will introduce the notation, and I will put it here because we will start with some Gaussian vectors, but then for a long time we will forget about them, so just for future reference. But this Hn is a random subspace of codimension D, so its orthogonal complement is a random subspace of dimension D. It can be obtained as a span of D IID standard Gaussians. So we have G1 up to G IID standard Gaussians in Rn. And then to use this volume formula, we need an orthonormal basis. So with Gram-Schmidt, we get to U1 UD, orthonormal basis. And then we have U1 transpose. Our vectors will be vertical. And this is D. So we start with those Gaussians. You do the Gram-Schmidt orthogonalization, obtain UIs, put them as rows, and VIs are the columns. So the good point about this formula by Nair and Koch is that in the end, even though we analyze a high dimensional section, we end up in fixed dimension D. In those formulas, we will be looking later in fixed dimension, and it will allow us to use some tools, not so much from high dimensional probability as from, let's say, classical probability. So the formula we want to use tells us that up to some factor which depends only on P and D, our normalized volume is the expectation, I should say conditional expectation here, of this random variable, where now, for simplicity, let me denote xj as the reciprocal of wj. And wj are those IAD variables related to the stable distribution, independent of the i's. And yn is such a determinant. So here it means this subscript x that we integrate only with respect to x. So if you wish, take the conditional expectation with respect to the Gaussian variables. Okay, so this is this determinant. We can use Cauchy-Binet to expand it in this way, where those AIs, I should cover it a little bit. These are, okay, so here this notation with underlined D means that we sum over all multi-indices with pairwise distinct entries. So in the Cauchy-Binet, these are increasing entries. And here we look at all of them. That's why we divide by d factorial. It will be just more convenient later on. But the point is that those AIs are determinants squared of d by d matrices obtained by selecting d columns from the matrix formed by our orthonormal basis. And what is important is that those AIs depend only on the Gaussian variables and are therefore independent of those xi's here. And a few comments about it. So here I just recall it again. We want to take expectation with respect to x. So of course we treat AIs as constants. Here we have independence and they have the same distribution. So for each summand, the expectation will be just AI times this mu, the expectation of a single x to the power of p. And if we did the Cauchy-Binet formula without those xi's, just putting them to be equal to 1, then because our matrix is formed from an orthonormal basis, we would get 1. So even though those AIs are random, there is some restriction on them. They add up to 1, which in particular means that when we integrate this y with respect to x, we will get mu. So the average here is independent of, I mean, it's a constant, does not depend on these random coefficients. And now we use, you might call it, well, I don't know, you can call it Taylor expansion, because we have, this is an explicit formula, this is just equality. So we tried to use some, I don't know, Lagrange remainder or something, and somehow we were not able to finish to conclude, maybe we missed something. So in the end, we decided to just write such an ugly formula. And now when you look at the linear term and you integrate it, then because of this quality, you will see that the linear term vanishes. So this function gives you something like that. And now, it turns out that only the first term contributes here. So the remaining two are of smaller order than the fluctuations that we want to prove. And again, one may wonder if this expansion is not too much. Perhaps we should have expanded up to, well, one degree less, right? Up to order 2 and have the remainder. But then again, we were not able to do it. This may have something to do with the reasons why this second and third terms vanish in the limit. So for this term, it is just some explicit expansion, right? So this is the central moment, but not absolute central moment, but just the central third moment of a random variable, which is of mean 0 after we subtract mu. And this random variable is a sum of many random variables. They are in general dependent, but there is a lot of independence still between them, right? Because all the time, for now, we are looking at it, thinking of AIs as fixed. Right? So the randomness for the moment comes from those X's. So if you look at such products for two indices which do not overlap, then they are independent. So when you expand it into a triple sum and integrate, a lot of things will vanish. And when you look at overlapping indices, triples of indices, then of course there are not so many of them. Now we go back to those AIs, and this is the second ingredient that we need here. It's very easy concentration on the sphere. So recall that those AIs were some determinants of d by d matrices whose entries were taken from such a matrix which was formed by a random orthonormal basis, right? Or not orthonormal basis, but a random set of d orthonormal vectors, right, in Rn. So in fact, each of those rows is distributed uniformly on the high-dimensional sphere. So we know that the coefficients are at most square root of log n over n, right? This is the maximal coefficient, right? So on average, like, they are roughly 1 over square root of n, but concentration gives you that the maximal one that does not increase by much. So when you take this into account, together with this accounting of bookkeeping of those overlapping indices, you will see that the first term here, this third moment, vanishes. And the last one is more problematic. Well, first of all, this is perhaps not a big abstraction. We have those unpleasant powers in the numerator, but what is more troubling is this square root in the denominator. Right? And for this, one needs some comparison. I don't know if one needs, but this is how we did it. Some comparison of moments for polynomials. So some of them are classical and go back to Krakowiak and Szulga, to results from the 80s. And we needed one more, perhaps it's too big a word, but in the spirit of reverse hypercontractivity result. So let me very briefly tell you what it is. So I'm not going to get into hypercontractivity here in the details. I will just mention a corollary to the general result. And let me say that the result actually is really much more general. It works for Hilbert spaces. So, and it gives explicit constants, behavior of constants. Here we don't need it. We just need constants to be independent of the dimension n. Right? So we look at polynomials in n variables, and I should perhaps define this notion because various names are used in various areas. I will call a polynomial tetrahedral if it's a polynomial of many variables, and it's tetrahedral if it is affine in each of them. So there are no powers higher than 1. So it turns out that if we have such a polynomial in IID variables, which have kappa moments finite, then you have a sort of reversed Hölder inequality. The moments of order kappa can be bounded by smaller moments up to a constant which, well, depends on the law of the variables, but it's finite and depends also on the degree, but it is independent, what is important to us, independent of the number of arguments of the polynomial. And this other lemma does something similar, but for negative moments, and now it's just for positive random variables. So if we have such a polynomial with finite first moment and moment of order minus rho for some positive rho, then again, I could write it as negative moments, but we are using it in this form. So this formulation resembles perhaps more the standard version that appears in such hypercontractivity bounds, this constant sigma, which depends again only on the law of x, it is hidden inside the argument, but we will use it to, we will apply it to homogeneous polynomials, so then you can move it outside. So again, it's like reversing up to a constant, the Jensen's inequality. And when you go back to this ugly formula, let me just recall that yn, right? Yn is this first part here. Right? So it is a homogeneous polynomial in those variables xi. And xi's were reciprocals of random variables obtained from the stable distribution. And they had all negative moments and positive moments up to 1/2 plus something. Right? So now we are looking at reciprocals. So it turns out that we have all positive moments and we have more negative moments than minus 1/2, right? We have a little bit more. So this is good news for us because now we can just use Helder. So basically you use Helder here and trade all those ugly powers, all those ugly moments, no matter if they are negative or positive, you trade them for the first moment, and the first moment is just a constant. Right? So these are still just conditional moments. So the last part also is negligible in the limit, and we just have to look at the first part. So here again, like with the third moment, it is, well, the variance of a sum of random variables with a lot of independence. So when you just write it, this square as a double sum, a lot of things after integration will vanish. And, well, you will have a sum over a pair of indices, right, which may overlap. If they do not overlap, the expectation vanishes. If they overlap by too much, there are not so many of them, right, because of this overlap. So in the end, it turns out that what matters here, what survives in the limit, is just products of such ai, aj, where I and j are d indices, right? I1 up to id, which overlap just by one entry. And then, well, until now, all we used about those AIs was that they add up to 1, right? And that they are small. Now we are going to recall what they were. So they were determinants of submatrices of this matrix. And this matrix was created with Gaussian variables. So let me now write one more piece of notation. When you put the original Gaussian variables as rows, then we will denote the columns, which are again d-dimensional. We will denote them by gamma. And when you take all these combinatorics here into account and recall that those UIs were obtained by the Gram-Schmidt orthogonalization, it turns out that in the end, up to some factors, the variable you want to study is such a ratio, Sn over Vn. What is Vn? Vn is the product, well, raised to the power, but it's a product of subsequent normalizations in the Gram-Schmidt decomposition. So it is not difficult to handle this, because recall that those GLs are standard Gaussian and IID. When we look at the ELF factor conditionally on the previous variables, G1 up to GL minus 1, the ELF factor is just a projection of a Gaussian variable onto, orthogonal projection onto, well, a random subspace, but independent random subspace of dimension, I think, n minus L plus 1. Right? So it is again a Gaussian vector, and here we are looking only at lengths, right? So it's quite easy to analyze it just by subsequent conditioning. And the numerator here, well, it is written in an ugly form, but in the end, it's just a symmetrized version of what I told you before. You look at two selections of D columns from your matrix in such a way that they overlap just by one column. And then you look at the product of determinants. So this is just the bottom. It's just written. If you have two sets of D vectors, but they overlap by one vector. So together you have 2D minus 1 vectors, right? And what is written here is just all possible ways in which such vectors can be split into two sets which overlap just by one vector. So I guess there's no need to focus on this. What is perhaps important here is that random variables of this form are very well studied. This is what is known as U statistic. So the next talk is going to be about Poisson U statistics. So this is the classical counterpart. So just a sum of a fixed function of say D arguments over all possible choices of arguments from the sample without repetition. Right? We have this underline here. So in our case, it is a U statistics of order 2D minus 1. And the arguments are just independent Gaussian variables in RD. So when you do this conditioning here, you will see that this denominator, we have the leading term, and then we have term of order 2D minus 1 times a sum of independent high-squared centered random variables, plus something of smaller order. As for the numerator, there is this general theory of U statistics. It all goes back to the 40s, to Hevding and Halmosh. So it is known that each U statistic can be decomposed, well, square integral U statistics, into uncorrelated terms, and each of such terms is again a U statistics, but of different order. The function has different number of arguments. And it doesn't matter, these are some orthogonal projections, it doesn't matter what they are. What is important that it's the first non-vanishing element in this expansion that dominates the whole sum. And in our case, it is already the first one. So this is some, you see, you have to integrate out most of the variables, all except for the first one, and subtract the expectation of the whole thing. This is known as the first Hevding projection. And then when you take all of this into account, you will see that this normalized random volume is just such a quotient of two variables which you control, right? They have some leading deterministic term coming from expectation. And then they are basically sums of independent random variables. So jointly, this numerator and denominator, they converge to a two-dimensional Gaussian vector. And what you just need to do is to use again some geometry well, first you have to find explicitly this P1H, and then you have to find the two-dimensional covariance matrix. So it's again some properties of Gaussian distribution, but this is a little bit tedious, but rather standard, and it allows you to finish this proof. So this is basically the idea. And well, let me now pass to the softer approach for the equal to 1. It will be, it will still use some unpleasant notation. I apologize for it, and some tools, but it will be of a different nature. So again, we have our subspace Hn, random subspace. It's of codimension 1, so the orthogonal complement is just a span of a single vector. And again, we want to represent it in law. This is a vector uniformly distributed on this field. Right? So we want to represent it in law by Gaussian random variables. But now, for technical reasons, we want to do it in a somehow consistent way. So we start with an infinite sequence of GIs. This has to do with the tool, formulation of the tool we are going to use. So we have an infinite sequence of GIs, and we just normalize the vector formed by the first n of them. Right, so this is our uniform vector of the sphere. And the Chasapis-Maillard-Koch formula tells us that the normalized random volume we are looking at is just the conditional density, we treat those GIs as fixed, right, of such a linear combination of our variables y, where y are IID with this density. So we want the density at 0. Well, so it is a sum of independent random variables, so it makes you think about the local limit theorem. But local limit theorem would give us just the first order approximation, which in fact we already know. We need to look at an expansion, right, of the density, which is known by the Edgeworth expansion, right? So there are such expansions either for the cumulative distribution function or for densities. What is problematic in our case, and it makes things slightly unpleasant, is that we are looking at a version for non-IID case, because our normalization here depends on I. So let me state the theorem. Maybe first, sorry, the Edgeworth expansion. How does it work? So we start with independent mean zero, I should say, finite variance, random variables. We look at this variance Bn, and then we create some coefficients which involve the kth cumulants. So this lambda depends on k, the order of the cumulant, and n, the cardinality of the sample. If they were all IID, it would be simpler, because you see Bn would be then expressed as n times a single expectation, and also here we would have n times a single cumulant, and lambda would be independent of n. But in our setting, it does depend on n. And then we create some functions with a rather unpleasant formula involving Hermite polynomials. So, well, this is just copied from the book, right? To be honest, before this work, I had always been trying to avoid Edgeworth expansions. But here I had to look at the book the classical book by Petrov, two books on sums of independent random variables, and it's a theorem. I think it should be attributed to him. So I don't want to torture you with all those assumptions. There are some assumptions. So the variance of partial sums should have a linear growth, right? At least. There are some moment conditions. There are some conditions like Lindeberg type conditions, and there's a condition in terms of characteristic functions, but fortunately it can be reduced to a different condition, which I don't want to write down here, but which can be verified. I will comment on it later, which can be verified rather easily in our randomized setting. And if all those conditions are satisfied, then this Sn admits continuous, in fact, density, which the normalized partial sum, right, which is like the Gaussian density plus a correction, and the error is of polynomiality decaying order here, right? So the fact that we cannot prove results in Wasserstein distance here is because in this theorem this error depends on the distribution here and is implicit, right? So we will just have some pointwise error which will be random, but we do not control it. In fact, this holds even uniformly in X. Okay, so this is the theorem, and the random variable whose density we want to calculate is given like this, and we think of those GIs as fixed, right? So when we calculate the density. So this is almost like the normalization by the variance of the sum. You have to divide by the standard deviation of those y's. Right? So we apply the previous theorem to xi equal to gi yi, and we apply it conditionally on gi. And now it turns out that all those ugly conditions, assumptions in this theorem, reduce basically to two facts. The fact that y's have nice density, and the fact that we have the law of large numbers. So let's show it only on one example. Like you see, we have such a condition, 1 over n sum of those expectations. But in our case, this expectation is taken only with respect to the random variable y. So what you have here is just 1 over n, the sum of k powers of your Gaussian variable. This is finite by the law of large numbers. And similar things happen for the remaining things. So you don't have to use anything quantitative, it's just the law of large numbers. So the Edgeworth expansion works. And one more nice thing when you look at those in principle quite ugly formulas is that yi's are symmetric. So some of the cumulants vanish, and we have just the Gaussian part and the part Q2n, right? And we expand, we use the previous theorem with k equal to 5, right, to get something of the order 1 over small little o of 1 over n to 3 halves. So then you see that this density at 0, which is the random variable you analyze, is just something like that. This is a random term of this order almost surely. And now you just have to analyze this, which is, of course, maybe slightly tedious, but straightforward, just with the central limit here. So in fact, this ratio appeared also in the previous proof, but there we had the general case of general D, and we had some determinants and Gram-Schmidt orthogonalization. It would it be so obvious that it appeared there from the notation. But if we have D equal to 1, so we have just one vector, and all we do is to one Gaussian vector which we normalize, then this is exactly what appeared there. And now you calculate it. And the proof for the cube is the same, but now you use the fact that it simply corresponds to a product distribution to uniform random variables. And the interpretation in terms of density holds not just for the central section, but for all sections, right? So that's why you basically follow the same proof with those yi's replaced by the uniform random variables. Okay. So what about d greater than 1? And p greater than 2, when we do not have the result. So in this softer proof, we use basically two ingredients, the volume formula and the Edgeworth expansion. So the volume formula works for general D, this is how I stated it, and the Edgeworth expansion, well, there are results which give you the Edgeworth expansion. There is a whole monograph from the 70s, but somehow they are not suited to our purposes. And I believe, to be honest, since we do not have this Edgeworth expansion, I didn't verify how the end of the proof would work, but it seems that once we have this expansion, we would probably just jump into something similar as the end of the previous proof, without the need to use hypercontractivity and like the first technical part. The problem here is that first, those results, the assumptions are quite complicated. But another problem is that they are formed, like in this Petrov's result, for infinite sequences of random variables. Well, it was okay for d equal to 1. Our random vector distributed on the sphere was obtained just by taking the first n variables of an IID, infinite IID sequence and normalizing them. Here, for higher d, we have this Gram-Schmidt decomposition in between, right? So somehow the partial sums you are looking at in consecutive steps, they do not come from the same sequence in some sense. And because of that, most probably, you would need rather a result for triangular arrays. And, well, I believe that this is doable but unpleasant. We didn't want to get there, especially that I have good candidates for people who could perhaps do it for us. In fact, such randomized central limit theorems appeared for the first time in the work by Sudakov in the 70s. But in the context of Klartak's result, the interest was revived somehow by again, Boaz Klartak and Sasha Sodin 13 years ago, and they considered like the very assumed bound for such randomized sums, and they observed, this was a nice observation, that the error, like in an average direction, the error of Gaussian approximation is, I believe, 1 over n and not 1 over square root of n, like in Berry-Essen theorem normally. So that's why it attracted attention, and in particular this Bielefeld, Minneapolis school published a lot of papers in this direction, which culminated in a book published last year. But they also have, like Sergei Bobkov has, results on Edgeworth expansions, which seem consistent, let's say, with what we were doing here. They are similar, but they focus not so much on densities as on cumulative distribution functions under milder assumptions on the variables, right? But still, well, I believe that it should be much easier for these people than for us, right? So, okay, and let me conclude by some problems. So, of course, well, I already mentioned it, we would like to extend it to any fixed d, but then the first order, well, assuming that you have it, or looking just at the case p smaller than 2, the first order results hold in much greater generality, right? I'm not mentioning even the fact that they hold for general convex bodies, right? But they hold for dimension which may increase, okay, in our setting, codimension, which may increase with the dimension like n to some power, small power. So the question is whether you can obtain some second order theorems when you allow the n to go to infinity at some slow but explicit rate. Then you may think about generalizations. Well, it's not clear to what classes one should generalize, but those that resemble the lpn-balls most are, for instance, Lorentz balls. And here I would be quite optimistic because Zachar Kabluczko and co-authors have a recent result in which they present many probabilistic representations of the uniform distribution of such balls. And originally, for BP-n-balls, such representations go back, I believe, to Sheckman and Zinn, and then to Barth, Gedon, Mendelssohn, and Naor. And they were not mentioned here, but they lie underneath the second volume representation formula, which I showed you. So I believe that starting from this work, one should be able to analyze this. And then there is the case of general Orlich balls, so unit balls of spaces corresponding to Orlich functions. And this is an interesting class of convex bodies, but in general, the results for them are much harder than for, well, are easier than for general convex bodies, but are much harder than for BP-n-balls. For example, there are some negative association properties and inequalities like this. But this is perhaps the natural direction if one would be interested in something like continuing. Okay, so that's it.